Hi, welcome back. um, Mini review of what we discussed before lunchtime about amplitudes. You saw in the open string case for tree-level amplitudes that there is a nice color decomposition, where you can squeeze all the dependence on the Chan pattern indices A into traces of the respective matrices capital T, the generators of UN. And I really wanted to stress the implications and value for field theory purposes. I mean, already at alpha prime goes to 0. I mean, these tree-level amplitudes of open strings reduce in the low energy limit alpha prime to 0 to gauge theory amplitudes. So therefore, color decomposition is possible in gauge theory as well. And this was actually quite a surprise, because gauge theory Feynman rules per se give you these structure constants, the FABC. And here this is a slightly different organization of gauge theory amplitudes, not in terms of contracted FABCs, but instead in terms of traces. So already the color decomposition alone is quite a valuable organizing principle for gauge theory, because the big amplitude with all the polarization and color degrees of freedom are then chopped into smaller pieces. And what I didn't stress in the lecture, I mean, amplitudes are for their living gauge or diffeomorphism invariant. Say in a gluon case, you can always send the polarization vector zeta to a momentum. You promote it to be pure gauge, and this should kill the amplitude. So amplitudes have to be gauge invariant in the sense that they vanish once you go from polarization to momentum. And similar thing for gravity, or the polarization 2 tensor. Yeah, and since the traces are linearly independent, already these partial amplitudes have to be gauge invariant by themselves. Yeah, so this is always good, to organize a bigger object into smaller pieces which individually have that symmetry. And this is particularly valuable at loop level, where the color decomposition is augmented also by products of traces. So a maximum number of G+1 traces at genus G, because the underlying open string worldsheets can have up to G+1 boundaries. Yeah, and what I didn't manage to cover concerns a revisit of the closed string amplitudes written in terms of open string amplitudes. So this is the tree-level underpinning of the slogan that gravity is gauge theory square. And this is a tree-level established relation exact in alpha prime. So it's underselling if for tree-level purposes you say gravity and gauge theory. Yeah, and these squaring relations, they go back to Kawai, Levelle, and Tai. I mean, the monumental paper on this was written in '86. And the actual form of the squaring relation between open and closed string tree-level amplitudes, it involves the color-ordered ones, or the partial amplitudes on the right-hand side. So imagine you have evaluated the partial amplitudes on the open string side, no color in here, then if you square them in the right way, you get closed string amplitudes, and well, the only ingredient in that squaring prescription is a kind of kernel, the KLT kernel, that tells you how to weight the different combinations of permutations here. And no color anywhere, one polarization here, another polarization there. So in case of the massless case, you sort of get two polarization vectors, and those, for each external state, will make up the polarization tensor of an individual closed string state. So here I've written the indices as if we were at the massless level, but also for arbitrary higher mass levels, the closed string polarizations are representable through such outer products of open string polarizations. And it's then up to you to project to the specific Lorentz irrep that you're interested in, say at the massless level. You can still project these outer products either to gravitons, symmetric traceless, or to dilatons for the trace, or the B field in the antisymmetric component. So this double copy prescription always gives you more than just gravity. Yeah, and finally, this kernel is made of trigonometric functions that go like sine of alpha prime p dot p, so no polarizations at all, only momenta, and it's in the end of the day an exercise in complex analysis, contour deformations, and tracking the monodromies to determine those. Okay, so these are the things one could elaborate more on gravity versus gauge theory. Oh yeah, and most importantly, I wanted to refine that slogan that I probably mentioned in the introduction and which is manifested by that formula here. So maybe a more accurate version of that slogan is that you divide out by color, because after all, this is about the partial amplitudes, the color strip ones that enter on the right-hand side. I mean, it's almost a no-brainer. I mean, it's clear that since gravity is colorless, that you don't square the color along the way. But it's this notion of color decomposition and focusing on the partial amplitudes, which is driving this KLT version of the double copy relation. Yeah, loop-level versions are a topic of active investigations. There is a reformulation of that double copy paradigm, which works in field theory to very high loop order. And getting this to fly in a string theory context with manifestly gauge invariant building blocks, it's a bit harder. All right, but now I really want to get into the superstring before time is up. So my apologies that I can only cover for time reasons the RNS formulation, but it would be really exciting to look into the pure spinor analog. Oh yeah, I wanted to recommend some video lectures given by Thales Azevedo at Perimeter in 2018. I hope this is easy to Google. Thales Azevedo, Perimeter, April 2018. I hope this uniquely specifies. Good. How to do a crash course of the RNS formalism in approximately 1 hour. That's not the easiest task. Let me try my best to give you a brief walk through some of the key features. So the worldsheet variables, let me specify those of the type 2a/b superstring case. And if you want to get to the heterotic theories, you have to specialize some of the Lorentz indices to fewer or more dimensions. Yeah, so in the type 1, type 2 case, the key idea is to augment the Polyakov action for the embedding coordinates x by some superpartners under worldsheet supersymmetry. So you probably heard mostly about 4-dimensional supersymmetry the previous week, and maybe SUSY lectures of next week will also take you in 2 or 10 spacetime dimensions. I will talk about both 2 and 10 dimensions, and I hope I'm not confusing you by this. For the moment, I refer to 2-dimensional supersymmetry on the worldsheet. So when I say that these x's are getting a SUSY partner, I really mean a SUSY partner in the sense of worldsheet supersymmetry in 2 dimensions. Yeah, so this superpartner is here denoted by psi. This is coming from a worldsheet spinor. And the index mu is, you read it correctly, this is a vector index for Minkowski spacetime. So from the spacetime perspective, well, this is not a spinor in spacetime, only a spinor on the worldsheet. Yeah, and here, this is already the gauge fixed version. I mean, if you truncate it to the bosons, you get Polyakov action in conformal gauge. And there is a lot of additional gauge fixing going on in the background if you want to have such a simple form for the supersymmetric RNS action. So this is obtained from gauge fixing a more symmetric action. This is in so-called superconformal gauge. So the more symmetric action that got gauge fixed and that I'm not writing down can be found in section 8.2 of the Uppsala lecture notes in the references on the website. Yeah, this more symmetric action can be viewed as doing two-dimensional supergravity. I mean, Polyakov action before gauge fixing can be viewed as general relativity in 2 dimensions with a metric and matter field X involved. And now to get there, you start by supergravity, having a metric on the world sheet, but also a gravitino, some spin 3/2 field on the world sheet. And then X and psi are also present in this 2-dimensional supergravity action and somehow coupled to the gravity multiplet. And yeah, this gravitino can locally be completely gauged away. There is a lot of symmetry to this 2-dimensional supergravity action, namely diffeomorphisms and local supersymmetry transformations. Again, Weyl symmetry, and also a fermionic version of that known as super-Weyl transformations. So the 4 of them work together such that you can completely get rid of the gravitino locally, and again the metric can be sent into eta, alpha, beta form. And there is now residual gauge symmetry coming up, similar to that of the Polyakov action in conformal gauge. Namely, residual gauge transformations are diffeomorphisms and local supersymmetry transformations that can be undone by diffeomorphisms and super-Weyl. So this is worth writing out, the residual gauge freedom, because this was the gateway into conformal field theory in the bosonic case, and now this is taking us into an even more powerful version, into so-called superconformal field theory. So this is once more coming from the residual gauge freedom, superconformal transformations, which are diffeos and local SUSY that can be undone by Weyl and super-Weyl. Yeah, and to general superconformal field theories in 2 dimensions, the algebra is generated not only by the energy momentum tensor, but now there is a fermionic partner to it, namely the worldsheet supercurrent. So, as I said, energy momentum tensor and supercurrent. So those are present and the key players in any 2-dimensional conformal field theory. And here, where we describe the free boson together with the free fermion, in that case, there is an explicit realization, which, well, here you already know the first term. For energy momentum tensor in this particular CFT of the free boson is that one. And now that we have this extra field coupled in, I mean, if you go back to the supergravity action and vary with respect to the metric, you will also get some bilinears in psi, and the concrete fingerprints on the energy momentum tensor look like that. Okay. Yeah, and the supercurrent has a similar definition. Vary the supergravity action with respect to the gravitino before gauge fixing. And then you can still go to superconformal gauge after that. And what it is Yeah, it's, if you wish, the mixed contraction of the free boson and the free fermion. Yeah, so I've already told you about the central charge counting before. The presence of this extra fermion will, of course, have an impact on the quadruple pole of the energy momentum tensor with itself. So from these fermionic terms, you get a central charge combination of half a unit per component, per vector component, which leads to the total that I stated yesterday. It leads to a total of 3d over 2 central charge for this X plus psi system. D from the bosons and D half from the worldsheet fermions. Now, to evaluate the action of the superconformal algebra on the fields, I mean, I still haven't spelled out the SUSY transformations, to be fair. So in order to get the action on the fields, we need to know the OPEs. Well, those for the dx you know very well. And to make sure you can also get your hands on the fermion, this is the 2-point OPE that you can extract from the action. And this is like the driving force to figure out, a couple of things. For instance, that using this with the energy momentum tensor, you figure out that psi is a conformal primary of weight a half. And furthermore, you can determine the SUSY transformations. Yeah, I mean, just to be clear, we paid a lot of attention to the OPE with the energy momentum tensor, like in particular from conformal primary fields. The way it transforms the conformal primary is fully encoded in the OPE with T. So this was about the conformal transformations. And now, as part of the superconformal symmetry, there are now these local supersymmetry transformations, and they are completely encoded in the OPE with G, the supercurrent. So for instance, in order to specify how X and psi are related by worldsheet supersymmetry, it suffices to write down the OPE of both with the supercurrent, which in full glory look like that. So acting on the boson, you get the fermion. You actually get it in both differentiated and undifferentiated form at different singularity orders of this OPE. Well, you have seen something similar in case of the energy momentum tensor OPE. And then similarly, if you act on the fermion, you get back to the boson with suitably chosen factors. So here then you get back to this. Oops. Good. This is a particular realization of superconformal symmetry. And with these properties, the doublet of fields here forms something which we call a superconformal primary. So this is the analog of a conformal primary, but now also with supersymmetry baked in. And yeah, the notion of a conformal primary was the key to construct vertex operators and to describe the spectrum. And we do exactly the same for the superstring. We want vertex operators to also form superconformal primaries, a bit better than just being conformal primaries. So this is the key guiding principle to construct the space-time boson part of the physical spectrum. So my plan is to go through the spectrum in 2 steps. First doing the space-time bosons, and after that doing the space-time fermions. And I will do everything for open superstrings. I mean, you saw it for the bosonic strings. It was much less of bookkeeping work to describe the open string states, because then mass level by mass level, you just double copy all the polarizations to get those of the closed string. And that double copy property or connection between open string spectra and closed string spectra, this goes through to the superstring. So to be on the easier side, I do everything for open strings. Yeah, here is what I already said, that physical states, you want to one-to-one map them to superconformal primaries. So only the prefix super is new in comparison to the bosonic string. And okay, here is one example of a superconformal primary, a doublet of weight 1/2 and a doublet of weight 1. And for the purpose of vertex operators, we want to have more general such doublets of fields, which are again conformal primaries with a old school conformal algebra. So primaries without super. So these are primaries with respect to the T that also contains the fermionic term now. But this is not the end of the definition. In order to be a superconformal primary, it needs to be a bit better than just this. So we impose the generalization of these properties on the two conformal primaries phi minus and phi plus. So let's call the phi minus the bottom component of this doublet. Bottom because it has a lower conformal weight. And that bottom component should be taken to the top component. And conversely, the top component should be transformed in the following way. It takes you back to the bottom component. And there's again a coexistence of undifferentiated and differentiated. Okay, so this is what we expect from a conformal primary of these conformal weights here. You can, of course, also define a superconformal primary with more general values of these h's, but I'm already focused on vertex operators. I want that we can later on do a d square z integral and get a diff cross Weil invariant. Hence, I'm only interested in superconformal primaries with this choice of h. Good. So now, to get closer to the construction of the vertex operators and to the determination of the spectrum, let's once more decompose into plane waves and the rest. So this is completely analogous to what we did for the bosonic string, only that our Greek alphabet is getting a little bit too small. So there will be a plane wave to make sure that we get a momentum eigenstate, and I'm once more using some notation for everything else, this capital Xi. This is taking care of everything which is not a plane wave, namely, which only has differentiated x's and psi's. And actually, these psi's can be undifferentiated. So I hope this is still readable, that the number of z derivatives can also be 0. Okay, these are the construction rules. Plane wave and any such combinations of differentiated x and potentially differentiated psi's. Okay, and now what is allowed within these decorations? So a very important truncation or prerequisite is the so-called GSO projection. For the moment, I will have to state this as an unmotivated rule, but I hope I get to the point towards the end of the lecture to motivate it from locality of the operator algebra, namely to avoid getting branch cuts as vertex operators get closer together. So we impose this psi, or the physical states, to obey the GSO projection, Gliozzi, Scherk, Olive, which goes as follows. We want that there is an odd number of psi's in total. So loosely speaking, the worldsheet fermion number should be odd. And just to be clear, it doesn't matter how many derivatives, so all of them have fermion number 1. So the total number of psi's that I want to have in a vertex operator should be odd. This is GSO projection. Yeah, with this extra rule, the admissible values of H go as follows. I mean, this decoration psi can then only have conformal weights that are a half, if it's just a single psi, and then odd fermion number will only allow for such half-odd integers for this respective H. Okay, and now we are almost there to read off the masses. So the requirement was that we want to have conformal weight a half for that one. And this conformal weight a half has contribution alpha prime p square from here, or minus alpha prime m square. And I just told you what the discrete choices are for the H of this decoration. So doing the same kind of rearrangement that we did in the bosonic string case, you can see that the masses are given like such, and with the admissible values of H psi, this is an integer multiple of 1 over alpha prime, non-negative. And yeah, this illustrates how the GSO projection rule eliminates the tachyon. Maybe this is a 0th order motivation, why to do that. So why does it eliminate the tachyon? Well, if it wasn't for GSO projection, the first attempt for this psi would be just 1, which has fermion number 0. Of course, we are disallowing that, but just in case you were to take H psi to be 0, namely for the identity operator, then you would have a negative m square. Yeah, so no tachyon in there. And then the simplest choice you can make for this decoration psi is giving you a massless state. Namely, this is coming from the choice where, well, you put a single fermion in a minimally invasive form. The simplest choice is having a single psi, but since it has a vector index, mu, you need a vector to soak that up. So the simplest states compatible with GSO projections have polarization vectors. And for instance, give rise to the following spelled out version of that bottom component field. Here recombined with the plane wave. Okay, so this is supposed to be the bottom component of a superconformal primary, but is it really superconformal primary? I mean, if I hit it with G, I want to have a simple pole, but nothing more singular than that. So the real deal is that this superconformal primary condition, it forbids you to have a double pole, or also forbidding higher order poles. So this is maybe the particularly interesting content of that requirement. Superconformal primary. And let's see how this works for that expression up here. So if you OPE that one with a supercurrent, using the OPE for x that you know very well, and also using the OPE for psi that I just gave you, then what you will find is a double pole with residue psi.p. Okay, so this is something you don't want to see on the right-hand side of this OPE. So the mission is clear. Tune your polarization vector zeta in a way that this dot product here vanishes. So I very much hope that this looks familiar to you. This is the same kind of game where we found the transversality condition for gauge bosons in the bosonic string from imposing that the vertex operator is a conformal primary. And here it's about the requirement of having a super conformal primary, which gives rise to that transversality condition. Yeah, so this is a first step at the simplest bottom component of these primaries. I haven't told you how to get the actual vertex operators out of it, but let's wait for that for another 10 minutes. Let's also explore the top component of these massless states. Let's compute the associated top component. Denoted by phi plus before. This is conformal weight 1. And yeah, this I can generate dynamically by reading off the simple pole term in this OPE with a supercurrent. So if I impose this transversality constraint and expand one order higher, I can read off the top component. And here in the case of at hand, this top component will read as follows. This is proportional to polarization vector. And now this is a mix of two terms. First of all, there is something you have already seen for the bosonic string, the gluon vertex operator. But now it has a little extension by psi-psi. And of course, the plane wave. Okay, so this is the top component of this superconformal primary. And from this one, we can read off what kind of gauge freedom is hidden. So even if I haven't given you the actual vertex operator, it is probably not a surprise for you that total derivatives don't matter. So this one sometimes becomes a total derivative, namely if we choose zeta to be the momentum. So it's a total derivative in Z, and also in the superstring, such total derivatives will integrate to 0. Therefore, this choice of polarization here, which causes that phi plus to become a total derivative, this is giving rise to a spurious state. And it completely decouples from the rest of the spectrum. Okay, so this is not a physical degree of freedom. Now, how to see that this is a total derivative? For the first term, this is identical to the calculation in the bosonic string. Now, there's this new term with psi-psi, but in case of zeta going to p, this will just vanish. The reason is that psi is anti-commuting, and I would contract the psi-psi into p mu, p nu in case of the spurious state. So symmetric contracted with antisymmetric is 0. Or that term is gauge invariant from the start, the psi-psi term. If you want, you can view the coefficient of psi mu, psi nu. You can view this as a linearized field strength. Yeah, I think I already gave the spoiler. I already said the key words. These zetas, these polarization vectors, must refer to gauge bosons, because we once more have this transversality condition plus the freedom to add, to shift by a momentum. So we get gauge bosons at m square equals 0. And for instance, if we specialize things to be on a D9 brane, then it's 8 degrees of freedom. Yeah, as you can see, I didn't have the discipline to keep on using these Neumann direction indices, capital A, capital B. I was using mu. Maybe I'm mentally on a space-time filling D9 brane here. I apologize for that. And on this D9 brane, or space-time filling for 10-dimensional superstrings, the number of degrees of freedom here for the massless open superstring boson, that is 8. Okay, so this is the superconformal algebra gymnastics to get the physical states, but now how to get actual vertex operators from them. So the mantra is the same. We want to have a diff cross VIII invariant. This will again require us to integrate that vertex operator. And to get this to be diff cross VIII invariant, you want to have a conformal primary in the old sense of weight 1. And yeah, for the upper half of that superconformal primary, this is okay on the spot. This one does have by construction conformal weight 1. So that you can use literally as a vertex operator, simply by construction. But now, what about the lower component? So that lower component is lacking half a unit of conformal weight. And how can we complete this to be a conformal primary of weight 1? So now this goes into a similar direction as having an integrated vertex operator and an unintegrated one. You saw it in case of the bosonic string, that I can convert the integrated vertex to an unintegrated one by dressing it with a C-ghost. And a similar trick applies here. I need to dress this one with ghosts in order to get a good object that I can use as a vertex operator. And yeah, before writing down that dressing, let me give some general characterization of the ghost sector. So for the bosonic string, the ghost sector was the BC system, conformal weights 2 and minus 1. They appear in a path integral setting when you deal with a diff cross Weil gauge fixing in a careful way. And now, in case of the superstring, there will be yet another ghost system. This one will be Grassmann even. And it's strictly speaking coming from worldsheet spinners. So there are worldsheet Dirac spinners with components beta and beta bar, as well as gamma and gamma bar. So these are worldsheet spinners. And they can also be made to appear in path integral treatment of that supergravity action that I did not write down. So there is that huge invariance of diffeomorphisms, SUSY transformations, Weil and super Weil. And all of that needs to be gauge fixed. And there is a Faddeev-Popov superdeterminant arising in that process. And this ghost system, or the super ghost system as we call them, this is part of that Faddeev-Popov superdeterminant. But I will just give you the end product if you first evaluate that super Faddeev-Popov determinant and then go into superconformal gauge. So a lot of things disappear in that step of passing to superconformal gauge, and what you are left with is an action like that for the beta-gamma system. So these are the ingredients that we will use in order to promote the lower component psi minus to a vertex operator of conformal weight 1. Now, what we want is half a unit of conformal weight. Let's see how close this is to the CFT characteristics of the beta-gamma system. Namely, the beta-gamma system gives you a CFT sector where beta has conformal weight 3/2, then gamma has conformal weight -1/2, and the central charge is +11. Yeah, I think this I already told you when we discussed the total central charge cancellation in the superstring. I mentioned to you that the critical dimension d = 10 is determined by demanding that all of these 4 sectors cancel in the total central charge. And remember, this was the final formula like that, where the 0 occurs at d = 10. Yeah, so how does it relate to the missing half unit of conformal weight in the phi minus bottom component? Okay, none of them fit on the spot. You could be tempted to use a derivative of gamma, but let me say it straight away that this is unfortunately not working. So we need to tune the beta-gamma system a little bit more before we get the missing ingredient for the vertex operator. And actually, this is a change of field variables. Known as fermionization. So we rewrite or reparameterize the beta and gamma ghosts in terms of a pair of fermions together with a chiral boson. So the first time I saw that, I was shocked. It's, at the first glance, looks a bit counterproductive to trade fewer field variables beta gamma for more of them. Namely, now we have a total of 3 field variables. But this is nevertheless a convenient move in the bigger scheme of things, because now you can isolate certain combinations more easily. I mean, what we morally want is something like a delta function with respect to the gamma ghost. This is what we actually want to insert. But writing down a delta function with respect to a conformal field is really tricky. And the purpose in life of this fermionization is to find a useful representation of this delta function. Okay, so what happens here? There is this chiral boson phi, which works a little bit like the free boson X, with the only difference that it has a meromorphic 2-point function. I mean, for X, we saw the 2-point function that went like log absolute value square. And here, phi is required to be chiral in the sense that I only have the meromorphic ones, z minus w, and there is no z bar or w bar term. Okay, and now these other fields, eta and xi, these are fermions whose OPE goes like that. Yeah, and as a very general thing, whenever you are in a CFT and you consider a change of field variables, what is allowed, what is not allowed? The key requirement is that you reproduce the OPEs that you had before change of variables. So from the action of the beta-gamma system, you can extract OPEs, namely that beta-gamma have a simple pole with respect to one another. And the big yes or no question is whether the change of variables is good enough to accomplish that. So this is an exercise you can do for yourself. Check that this change of field variables reproduces the OPE between beta and gamma. And that is a signal that you're on a good track or that you did nothing bad. Yeah, and we will take advantage of this change of field variables to identify the missing piece that you want to give the phi minus to become a good vertex operator.
So eta and psi are fermions in the sense that they're Grassmann-Alt?
That's right, yeah.
And are they still spinors?
Okay, here we are already in conformal gauge. No, they are not spinors. Yeah, and yeah, good that you bring that up. I'm promising you Grassmann even beta gamma. There is some Grassmann odd ingredient here. What I should have also warned you about, this exponential here is in fact a fermion as well. You can do a similar trick for the psi's. You can bosonize the psi's. And then you must be careful to tune the exponents correctly, such that the OPEs have Fermi statistics. I think I will give you an example right here, or I think I will give an OPE from which you can see that this is... no, it's not on this blackboard, but I hope I can illustrate it nevertheless. Yeah, so this chiral boson we will use to produce a fermion, and in order to work out its CFT characteristics, we need to translate the energy momentum tensor of the beta gamma system into the energy momentum tensor of this chiral boson and that of eta psi. And interestingly, this chiral boson not only has the term that you know from the dx from the free boson, but instead it has a double derivative term. It has a very weird energy momentum tensor, and that in turn means that if I build an exponential, its conformal weight is not just the square of the exponent, but it has a shift, a linear shift in Q. So this is getting pretty close to the formula for the conformal weight of the plane waves. So there you saw a p square, the square of the momentum, the square of the prefactor in the exponent. So this q square term is the analog of p square. But now that the energy momentum tensor has a double derivative, there is a shift here. Okay, and now what kind of values are possible here? Or putting it differently, how can we tune that to give the desired conformal weight a half? There is a unique value of q which gives that, namely q equal minus 1 is doing the job. So q equal minus 1 is the sweet spot to get conformal weight, a half of that. Okay, I think there is an easy answer to your question from before. This is a fermion because it has conformal weight a half. So its two-point function is 1 over z minus w, which is odd under flipping z and w. Good, yeah, here this brings the long journey to an end. The vertex operator to use for the bottom component is the following. Address this h equal a half field denoted by phi minus. Dress it with a superghost contribution, namely that e to the minus phi, where the superghost charge is fine-tuned to get exactly the conformal weight that is missing. And yeah, as I was saying, this is sometimes informally referred to as a delta function of gamma of z, but this can open a big Pandora box to make it more precise. What does it mean to be a delta function with respect to a conformal field? Yeah, for each physical state, I have now given you maybe more than you would have wanted to. For each physical state, say a gluon polarization, I've now given you two vertex operators. Okay, this one is said to be in the ghost picture -1, simply because there is a super ghost ingredient which we didn't have in the earlier V0. So perhaps this is a bit unsettling to have two representations per physical state. Or two representatives. So this raises the question which one to use. Use the V0 version or use the V1 version. And how does your choice affect the amplitudes? Okay, there is a boundary condition set by ghost charges, similar to what we had in the BC system. We had a total of 3 insertions of the C ghost in tree-level amplitudes, and that was exactly the right amount of ghost charge to cancel the background charge of 3G-1 at genus 0. And there is the same kind of background charge going on for the beta-gamma system. There is a separate charge, maybe you want to call it super ghost charge, which enjoys an anomalous conservation law. And the general rule is, analogous to that of the bosonic string, that correlation functions in the beta-gamma system are 0 unless you fine-tune the super ghost charges. Or I will interchangeably say picture instead of charge in the case of the super ghost. Here you want to have 2G-1. So this is almost the 3G-3 of the BC system, but with an additional factor 2/3. But it's important to note, the background charge counting has to be done separately for the BC system and for the beta-gamma system. Yeah, so this kind of selection rule on the non-vanishing correlators at genus G, this is equivalent to saying that there is a background charge that you have to cancel. Okay, now this is meant to give you a partial answer to the question how to choose which of them you use for a given physical state. You have to use a fixed number of V-1s in a way that at genus 0 you have 2 of them in total, for instance. And then you can cancel the background charge and get a non-vanishing correlator. But then you may ask, which one of the 2 should I put into that picture? And here it's worldsheet supersymmetry that comes at your rescue. I mean, after all, the 2 fields in there are related by worldsheet SUSY. And if this is meant to be a symmetry of the theory, it doesn't matter how I distribute the supercurrent that take you from the lower component to the upper component. I'm sorry that this is not a more precise argument, but it's in the end of the day taking advantage of worldsheet supersymmetry. And a more rigorous proof that the tree-level amplitudes don't depend on the ghost picture assignment, that would require BRST quantization, which I am not covering. But I think the moral reason why this works, the moral reason why we can freely choose which of the 2 external bosons we put into that picture, this is due to worldsheet supersymmetry. Yeah, that finishes what I wanted to say about space-time bosons. And the leftover time I wanted to spend on the space-time fermions. And again, we are doing this for the open superstring, just to evade the double copy of all the vertex operators we identify. Yeah, it looks like a pretty complete story, how we described combinations of X and Psi and Beta and Gamma. where is room for additional states or additional worldsheet fields? Where is room for space-time fermions? And the opening idea is that these spinors psi have two possible periodicity conditions. I mean, they're only defined, every spinor is only defined up to a plus-minus sign. I mean, a spinor is never an observable or physical quantity. You need at least two spinors or even numbers of spinors to form something in a bosonic representation. So these psi's are allowed to pick up a minus sign as you go around the closed string. So there are two admissible periodicity conditions, and those in turn give rise to two admissible mode expansions. So where I'm getting to is that this psi field can be either periodic or anti-periodic under the closed string move sigma goes to sigma plus 2 pi. And I was proudly reporting when we went to the plane that the z coordinate of the plane is automatically obeying the periodicity property of closed strings. So it was important back then to be periodic. And yeah, back then we were not handling spinors. So the new feature is that now, given that this is a spinor field, it is okay if it picks up a minus sign under this move. So I will now write down the respective mode expansions that take you to one option or another. So the structure of the mode expansion is the same as what you saw for the energy momentum tensor with the LM modes, or likewise the free boson with the alpha modes. So we have these modes psi r, and they go along with different terms in the Laurent expansion. And if I want to be periodic, then we need to make sure that the exponent is an integer. But from the conformal transformation to the plane, there is this funny minus a half here. So we must make sure that the mode number r is an half-odd integer. So psi modes that have plus minus a half, plus minus 3/2, they give rise to periodic fields on the plane. This is the first option for the mode expansion. And here's the second option. If you want to be anti-periodic, then write down the same mode expansion, but now take different ranges for the mode number r. So in order to be anti-periodic, everybody in the Laurent expansion should be half-odd integer power. And that in turn translates to integers r for the mode number. Okay, these two choices are referred to as the Navier-Schwarz sector and the Raman sector, respectively. So these are the names that got smashed into the name RNS for the entire formalism. And this NS also explains all the superscripts that I was dragging along for the phi's. Maybe you already got nervous why the hell I'm putting an NS there, but we will shortly come across similar phi fields for the Raman sector, where I will need the other superscript. Okay, these two options are there for the mode expansion, and even though I didn't point that out, we were all the time before using the Navier-Schwarz sector. So if you don't introduce any particular tweak, you are landing in the Navier-Schwarz sector in the construction of vertex operators, because the Raman sector has a certain energy shift. You need a you need a primary of non-zero conformal weight to transition into the Raman sector. So what do we see that? In order to see that there's a kind of energy shift to the Raman sector ground state, let's look at the Virasoro generators or the contributions from psi to the Virasoro modes L. So this is essentially the same formula that I used to construct the Virasoro modes for the bosonic string, but here we are getting the contributions from psi to the energy momentum tensor. So this is the contour integral representation of the Virasoro modes for the psi contribution. And so far I haven't committed yet whether this is in the Raman sector or the Neveu-Schwarz sector. Now you can insert both of the mode expansions in here and see what happens, whether you are happy with the Virasoro modes and if they take the same form as the brackets for the bosonic construction. I presented you the Virasoro algebra of the bosonic modes. So this commutator, like here and there, you can look up the expression you found, and I'm not committing to the value of the central charge, but I would really like to preserve the form of how this Virasoro algebra looked like in case of the bosonic string. And if you do this exercise for the Neveu-Schwarz sector, then it will work flawlessly. Just plug in the Neveu-Schwarz mode expansion here, and you will get another Virasoro algebra, maybe with a different central charge, but it's exactly the same form as what you saw in the bosonic string. But in the Raman sector, there is a catch. You have to do a manual correction. You have to add something to L0, which, frankly, I would not have expected. So let me be more precise. Let's say you apply the Raman sector mode expansion, that's what the vertical bar is saying, and then you extract the zero mode, setting m equal to 0. Then there is definitely some piece that you expect, namely that one. But with this one, you won't get lucky. With this L0, you won't reproduce the desired Virasoro algebra of the same form as in the bosonic string, but you are off by some shift. Or you can fix the problem by redefining what you mean by L0. So you have to add a constant to it. So this constant is depending on the number of space-time dimensions. Yeah, so you need this energy shift. And this is the way to identify what kind of primary field generates the Raman sector ground state. So the true vacuum of the theory is a Neveu-Schwarz vacuum. And you need something which injects the conformal weight d/16 to get to the Raman ground state. Yeah, so as I just said, the interpretation of this finding is that the Raman vacuum is generated by a Virasoro primary of this conformal weight. And let's learn more about what this mysterious primary is. Let's most of all discuss how many of them there are. And there's something funny in the Raman sector, namely that the mode expansion also gets a zero mode involved, some psi zeros, actually a vector full of psi zeros. And all of these zero modes commute with L0, so they don't change the conformal weight. So it seems like the psi zeros, they rotate around different Raman sector ground states. So to get an even better idea of the structure of this Raman sector ground state collection, let's look at the anticommutators of these psi zeros. So as an equivalent of the OPE of psi with psi, you can find that the anticommutator of the psi zeros gives you Minkowski metric. So that's the famous Clifford algebra that you know from the Dirac gamma matrices. So loosely speaking, these Raman sector zero modes behave like gamma matrices. So therefore, the Raman sector ground state must transform under the Clifford algebra. Hence, the Raman sector ground state must be a spinor. But now, with respect to the SO1, D minus 1, or whatever the Lorentz group is for the indices mu and nu. So there must be a space-time spinor which generates the Raman sector ground state. So if here I'm meant to introduce a shorthand S of Z for the mysterious primary field of weight d over 16, and we are here learning that this mysterious field must be space-time spinor. So please don't confuse this with worldsheet spinners. Psi is a worldsheet spinor, but a space-time vector. And for this operator here, it's a different story. It is a space-time spinor. And worldsheet-wise, it doesn't even have statistics that fits into an even or odd paradigm. So let's look at it in d equal 10. And in 10 dimensions, the Clifford algebra leads you to Dirac spinors of 32 components. So in 10 dimensions, we start out with a total of 32 choices. So then in 10 dimensions, there is a Dirac spinor worth of Raman sector ground states, which you get by evaluating this field S at the origin. And I'm now adding a spinor index to that field S. Maybe I should have done so in the first place, but we didn't know back then that it's a spinor. Yeah, and it acts on the actual vacuum on the theory, and I should write an Neveu-Schwarz subscript to emphasize that the actual vacuum in the conventional sense is in the Neveu-Schwarz sector. And then it's an extra effort through the spin field to take you to the Raman sector. Oh yeah, I think I just said the word for the first time. This field SA is known as a spin field, which interpolates between Neveu-Schwarz sector and Raman sector. And in 10 dimensions, its conformal weight is 5/8. Sounds like a tough challenge to get a vertex operator out of that, but it will be possible. Yeah, and before we do that, let me just stress how to think about the spin field in relation to the two different mode expansions. So the spin field is deciding about whether psi is going to be periodic or anti-periodic. And switching between periodic and anti-periodic, this is a bit like crossing a branch cut. So what the spin field does for its living, it is opening and closing a branch cut for psi. So the simplest configuration that you can imagine is to go into the complex plane, have a spin field at the origin, have another spin field at infinity, and then get a branch cut for psi through the connection in between them. But yeah, let's get back to the actual spectrum construction before I'm getting kicked out of the room. So how can we construct vertex operators now that incorporate Raman sector information? So the vertex operators for the Raman sector, the missing ones, they contain a spin field. And since the spin field is a spinor of the 10-dimensional Lorentz group, you will get space-time fermions. I mean, here I'm really after physical states which obey the spin statistics theorem. So knowing that all the vertex operators correspond to spinors of the Lorentz group, I can be sure that this is about space-time fermions. Okay, so how do we construct the vertex operators? How can we balance out the conformal weights? How do we get from 5/8 to an integer conformal weight, h equal to 1? We also need a spin field for the ghosts, namely for the beta-gamma system. Oops. More specifically, we need something that opens and closes a branch cut for the e to the minus phi that we put into the Navier-Schwarz vertex operator. And in order to see how to construct such a spin field, let me write down the OPE of these chiral boson exponentials. So we used the representative at q equal -1 before, but here is the general OPE for arbitrary exponents q1 and q2. The exponents add up, and the relative, the power of c minus w is controlled by the product of the charges. Okay, and what you want is a branch cut. What you want is a half-odd integer power up there. So more precisely, to get a branch cut for this one, which we have in the Navier-Schwarz vertex operator, you need the following spin field. So the salvation is use an exponential of phi with exponent a half, or plus or minus a half. So this is the missing superghost ingredient which you need to put into a fermion vertex operator. So this is the clue to get two vertex operators per physical spacetime fermion. There are again two ghost pictures, or at least two ghost pictures. There's even a third one, which I don't have the courage to mention. So per physical fermion state, there are the two options to insert it via V plus a half or V minus a half. And the first characteristics is that V plus minus a half will have one of these two spin fields for the ghost system. This is to say that per physical state, there are the following two vertex operators. With a ghost contribution I advertised, and then the rest is again made of the matter fields. So here I'm trying to be consistent with the notation for the spacetime bosons. So this phi Raman takes the analog of these phi Navier-Schwarz from before, which previously were of conformal weight a half and 1. And yeah, there's something else which we crucially relied on in the Navier-Schwarz sector case. So there, the two phis were related by supersymmetry, by modes of the supercurrent. So back then, we had the following rule. If you want to reach the upper component, then start at the lower component and apply the supercurrent mode G minus a half. So we want to do something similar now in the Raman sector. I mean, we have two different choices. They should once more be related by supersymmetry. But now we are in the Raman sector and have modified the moding. I mean, the supercurrent is linear in the fermion psi. So the Navier-Schwarz sector or Raman sector choice for psi directly goes through to the supercurrent, G. So in the Raman sector, there is no G minus a half anymore. So the best you can do is to use the integer mode G minus 1 to relate those two fields phi. So it's essential to tie together these two fields because they should satisfy the same physical state. I mean, if they are not related by a symmetry, then there's no hope that they're going to give the same physical state. So like this, you ensure that worldsheet-SUSY helps you to find one of the in the same state described by these two vertex operators in different ghost pictures. Okay, we are almost there. So this is the analog of being a superconformal primary, but more tailored to the Raman sector, where you don't have a G minus a half, but a G minus 1. And I think the last pieces of information that I should give you before closing is how do you select the physical states? Or what's the analog of this primary condition that vertex operators shouldn't have too high poles with respect to the supercurrent? You want these vertex operators to be conformal primaries of weight h equal to 1. And this is potentially in trouble for phi plus for the following reason. So this vertex operator in the higher ghost picture can only be a conformal primary if the G0 mode annihilates the lower component. So it takes a minute or two to disentangle that statement, but you roughly speaking need to use this commutation relation to see that should better vanish. Okay, and this is the way to find the field equations for the spacetime fermions, which among other things contains the massless Dirac equation. So the vertex operators in the Raman sector, or their matter contributions phi, have to obey this condition here. Okay, so this is essentially forbidding a pole of order 3/2 between G and the phi field. And this is analogous to what we had before. In order to derive the transversality condition for the gluon, we disallowed a double pole in the OPE of G with the vertex operator. And here we do the same with a slightly different power, 3/2. Okay, so now we can read off the masses from everything on the board on the Raman sector vertex operators. So there is a big bunch of things universal to the entire Raman sector, to the entire mass spectrum. Namely, they all have a spin field, both for the psi field and a spin field for the ghost system. They all have a plane wave. We are still after momentum eigenstates. And finally, there are some differentiated x's and psi's. Good. How can all of this conspire to give you conformal weight 1? So first, some good news. The spin field parts are already in perfect shape. So the fractional conformal weight of the spin field for matter is compensated by the fractional conformal weight of the ghost spin field. So the latter has conformal weight 3/8. Then there's the plane wave. Its conformal weight depends on the masses. And finally, there are these oscillators which have somewhat controllable H. So naively, you would say that it can appear in half-odd integer units. So naively, you would say perhaps it's a half, perhaps it's 3/2. But no, we are in the Raman sector. This must be integer because you only have integer modes for psi. Okay, so with these conditions, you arrive at the admissible masses. Solving for this to add up to conformal weight 1 determines the masses for the fermions to be 1 over alpha prime times non-negative integer. And this is the same as in Neveu-Schwarz sector for the space-time bosons. Okay, this is necessary condition for space-time supersymmetry. No chance of having a supersymmetric theory if the masses don't match. So all the mass levels look like you can form supersymmetry multiplets from them. And yeah, that indeed works. Admittedly not obvious from what I could say today, but yeah, the necessary condition for space-time SUSY is met, and you can furthermore construct a supercharge operator that maps physical states to physical states. Yeah, and the last rule I should supplement is the GSO projection. There was this GSO projection in the Neveu-Schwarz sector, which looked very ad hoc before, which was stating that in the Neveu-Schwarz sector, we want to have an odd fermion number. And the analogous GSO rule in the Raman sector is quite interesting. It forces S to be a Weil spinner. So maybe I should use a different letter for Weil spinner indices. It was not a good idea to work with Dirac spinners. It would probably take me longer time than I have to demonstrate that. But yeah, you must constrain them to be Weil spinners. Dirac doesn't work. So let me just state the general reasoning. The general reason is you don't want to have branch cuts between vertex operators. If you were to have such branch cuts, the amplitudes would exchange non-physical states of the wrong mass level. So this is something pretty serious. You want to have no branch cuts among pairs of vertex operators, and this is the source of the GSO projection. In the Raman sector, it's you get the GSO projection rule from the Raman sector by looking at pairs of those. Take the OPE between the Raman sector vertex operator and another one, and you have a branch cut if you started off with a Dirac spinner S. And the GSO projection in the Neveu-Schwarz sector, which I had trouble to justify before, well, I'm not sure whether I will be able to convey the gist of the argument in more detail, but roughly you have a branch cut between the Neveu-Schwarz vertex operators and the Raman vertex operators if you don't impose the rule of odd fermion numbers in the Neveu-Schwarz sector. So it's based on this reasoning that the GSO projection can be justified. Oh yeah, sorry, GSO projection, it means to say. Okay, I should really stop. And thank you so much for coming, for all your interest and enthusiasm, for all the great questions. I really hope that the lectures were useful for you as a appetizer into further research adventures in string theory and related topics. Yeah, enjoy the free weekend and good luck for the third week of the school.